All right, coming up. And then we had 002. Let's save this. How's that? Am I running? No? Maybe? Let's try this. Okay. All right. We're back. Tough loss for Patriots fans last night. That was kind of like watching unstoppable force meets the immovable object. It was just back and forth defense all night, and then a little bit of excitement there at the end. Cool. Last time on Applied Mechanics 2, we left off on Friday. We were talking about the last kind of stopping mechanism. The idea that something's falling into something with friction, and we came up with this equation of motion here. Let me highlight it. Whoop. But with friction and gravity, they're both constant forces. Friction's a little weird because it depends on which direction you're going. Like if you change direction, friction also changes its direction. But it is constant. And for this problem, as it's just falling down, it's still constant. So last thing I asked about was, how much normal force do we need to stop this thing? And I'm sure you spent the weekend just like pondering this, Socrates style, just like eating grapes, having cheese, drinking wine, like, the normal force. How much normal force do I need on Monday? So what do we think? How much N do we need? Did you already find something?
I think it's 1 Newton.
So we think maybe 1 Newton. 1 Newton? 1 Newton? Big fan of a hypothesis. What do we want? Let's do it the opposite. Let's make a table. NA. So 1 Newton. All right. Give it a. You could either try just plugging in 1 Newton, or try to come up with your own answer for N. But if we have 1 Newton, what is our acceleration? Did you come up with 1 Newton too, or you wrote it down? You wrote it down, Zach.
Okay, so 981 newtons. The acceleration cancel because it goes. Well, but it makes it so that it's constantly going up. It sets the acceleration to 0. But it makes the acceleration negative.
So I think it's just the gravity times mass divided by because our acceleration needs to be negative. Or I guess in my case it needs to be positive.
I figured out what's there. It's because we're rolling for a negative acceleration. We're not coming back because the velocity is directions. This equation equals this equation is going to count the back to the friction pretty much the critical point of this would be this critical point right here is its maximum distance. Because once it opens, that's where the negative acceleration sets the velocity to 0. But then because the negative acceleration continues now, we put the velocity in the opposite direction. Its position versus in reality,
In general, when we're trying to solve for normal force, we need the normal force and gravitation.
Oh, that's what you're talking about. Yeah, that's how I saw that. Yeah, it is point well, no. I think I did do that. Without, oh, yeah, that's there it is. Also, you're going right about the normal level. It does never hit 0, but it does come back. So, declare a normal first.
No.
It's not to do a point, 0.05.
Stop it. Does it matter?
That does
So actually, I did hear one other guess. I think one. Now I can't remember. Was it 5 newtons? Someone said 5. Did anyone say 5? 5? Yes. That is a great question. Like, how long? Okay. All right. So there's a great question, like clarifying question, like very engineering based of like, hey, I can stop this as fast as you want it to. How long do you want it to take? Like, do you want it to be, or do you want a certain distance, right? Like, we can specify it in different ways, but somehow there's, like, it's still an open problem. Like, n can be any number. And I asked a few people, like, what happens if n is too big? Like, what happens if you're trying to stop at a stoplight and instead of gently pressing brakes, you jam on the brakes? You stop suddenly, right? Like, now there's a large acceleration. There's not only a large acceleration, but there's a large change in acceleration. So, and that kind of comes back to this question of like, how long should this thing take? And there's different ways we can approach that. One way is kind of finding the bounds. So one of them could be, what's the lower bound? Like, what's the minimum force that we can apply to actually bring it to a stop? And then other one might be like maximum. There's no real maximum, right? Like, if we apply an infinite normal force, it's like this thing hit a brick wall, and it'll probably crush it. But that's a whole separate issue. So I don't have an answer for how long it's supposed to take.
But then if you applied like some incredibly small force, wouldn't it take like theoretically an infinite amount of time to stop?
Ooh, that is so. So what happens if normal force is too small? Was the next question. It might never stop. All right. So I said, so we had this guess of 1 Newton, and some people wrote that down. They're like, yes, that's also my guess. I'm like, okay, great. So what is acceleration if our normal force is 1 Newton? And I think some people, does anyone know how to find that?
What?
What is acceleration when normal force is 1 Newton? You know? Do you know what the number is?
Well, I know what it is when normal force goes 0.981.
0.981? Okay. Do we want to say it's 0.981 then?
Yeah.
All right. Let's call it that. 0.981.
Acceleration 0.
So acceleration is 0. Is that good? What's our distance to stopping if our acceleration is 0? Never? Why never? So we know, like, kinematic equation, at least in this case, friction, all friction is doing is changing the constant of acceleration. That's the thing that we're kind of learning about friction here, is that you can apply more friction, you can apply less, but it's not going to change the fact that it's still a parabola. But here, our parabola is not a parabola, right? Or is it? Am I missing something? If a is 0, x of t is whatever speed it enters our brake, that's how fast it's going to keep moving through the brake at a constant speed. So that's one, we found something. It didn't hurt anything. It didn't stop anything, but we also didn't build the brake yet, so we're still good. What other numbers do we come up with? Or do we want to go from there? Yeah.
Can you explain why it's 0.981?
Yeah. Does anyone know why 0.981, where that number came from? I was just taking it from the audience. Yeah.
Because our equation for acceleration is mu n over m minus g over 2, well, depending on how you times up and down, but u times n over m
Yeah.
minus g over 2.
So if I say 0 is g minus, oh yeah, I guess this one's 2 mu n, right?
Because the two walls.
2 walls, yep. So 1 times 1 over 0.1. Well, I guess we said that 0.981. So I'm taking my equation of motion, which says acceleration is the sum of the forces, where I have 2 times mu n and an mg. If I set those equal to each other, I solved a problem, but it's the problem of like, how do I put in enough friction that this thing stops free falling and has a constant speed? So this is our constant speed problem. Cool. That's a good start. So what else could we? Yeah.
So now any normal force greater than that number will eventually stop it.
Okay. So if we said n is 1, then it will stop. What is, 0 meter per second squared. Or you could use a different number if you want, but what do you think? How fast are we stopping with 1 Newton normal force? Slowly? Okay. Or if you want to use a different number, but we can fill out this table, or you can approach it a different way. But this was my thought. Like, we have different ideas. We'll write down what we have so far. Do you come up with a different number? Okay. Yeah. It's got to have some distance, right? Yeah. If we said it was like a brake pad.
Well, if I'm like grab, this is the acceleration.
Yeah, that's a good spot.
Oh, well, okay, good mistake. No, but that's the also just take the
One thing about the time is like if you know it took
and the graph says equations account for when the velocity equals 0, the friction will now it'll go flat. So right now, like it's the inverted parabolas.
yeah.
But is that just you have to account with the fact that when that's 0, that's why it stops?
Yeah, and there's different ways. Like you could create a Joseph's function, which would solve for when v is 0, and say from that time onwards, positions, or you can use like create an array, like even a chart. You figure out where's the max, here's the max, everything below the max is going to be. But you're right, like it's not a constant force, it's constant force, so you stop. Or at least all right, so we had more questions. It's so far it's more questions. Like no one wants to commit to like, oh well, I don't know. Do we want to stop it slow? Do we want to go fast? But one way is just like try a few ideas and see which one makes sense from like an engineering or design standpoint. So if we do the bare minimum plus a little bit. So 1 Newton, now we're stopping at 0.2 meter per second squared. It definitely slows down. Is it a positive 0.2 or negative 0.2? Negative. It should be negative. At least based on our free body diagram. We should be getting a negative acceleration. I'm pretty sure. If it's positive, then that means that we didn't apply enough force. So a negative. There we go. Did anyone try like a really big number? What other accelerations did we get? $15 seconds. 15 seconds is that the goal? It's got to stop in 15 seconds. That's what this one. Yeah, 0.2 would be fine.
That also takes 25 meters.
25 meters. Okay, so now we're talking about like distances, because we can also say v squared minus vf squared minus v0 squared is 2a delta x. So 3 squared equals 2, or delta x is equation 1, equation 2. So we can say roughly like 9 divided by 2, so 4.5 divided by a is our distance to stop. Again, just saying like if it's a constant acceleration, I can use those kinematic equations. So what was that, delta x? So this one's delta x is infinite because it'll never actually stop. How far do we go for 25 meters?
Yeah.
So with 1 Newton, we need a 25 meter long break. Like the size of the room. Is that good? It's a lot of like rubber to slow something that it's not moving that fast. Like it's not a rocket coming in for a land or a jet coming in for a landing, right? It's like it's an egg. Like we're designing like an egg catcher or something like this.
Have we yet to answer the question if this is even possible? Like, how do you determine the amount of normal force pressing on a cube dropping?
Yeah, so the question was how do you well, I guess there were 2 parts to the question. One was how do you determine how much normal force?
Yeah, you just change the width. Like, how does that work?
Okay, so one is like how do we determine what the normal force is? So one way is like based on our design that we're trying to do, we have to choose how much normal force we want. But then putting that into practice, like once we say normal force has to be whatever, 5.7 newtons, then I think the question is how do you apply 5.7 newtons? So one, at least from engineering kind of design standpoint, so at least what I would think, at least if I was going to design this, what would I do to stop this thing? I would figure out how much force do I need to get this thing to stop, then put springs in there, and the closer you put the 2 walls and the stiffer the springs, the more normal force I can apply as this thing gets into my stopping mechanism. So if this thing is like really wedging in between them, then maybe the physics are a little different because now the walls are like splaying outwards. But if it's just a little bit of deflection as this thing drops in there with some stiff springs, then roughly it's a constant friction stopper, something like that. At least that's how I would go about it. If you're, not that you asked like, how would you, Professor Cooper, do this? But that's how I would do it. Does that sound possible? Okay. There's probably other ways. Like another way could be, if you wanted to get fancy, you have an optical sensor with grippers. So as it breaks the optical feed, then grippers slam onto it, and then they apply a certain amount of force, and then it'll slow it down as it gets there. I like analog dumb things rather than adding like computational stuff, but maybe that's why I'm a mechanical engineer and I ride mechanical bikes. No electronic shifting. They look cool. I think it would be fun to have electronic shifters, like wireless shifting, but I love like mechanical levers and stuff. It's just something to do while I ride. Yeah, exactly. Okay. So that's kind of the how, like how could you even get this done? But the what do we want to do is sort of the missing piece. So on the one end, we figured out one thing we don't want to do is not stop it. So if our normal force is less than 980 millinewtons, then no good. It's not stopping it, so this whole thing doesn't work. What's another thing that we don't want to do? Or that you don't want to do? Not the problem. We're doing the problem. That one's sort of, we're already down this road. The boat has left. We're on the river. So we're doing the problem, but what do we want? What do we not want to do as we're trying to stop it? Crush it. Yeah. Too much normal force is not good. Okay. Yeah.
You could do an impulse calculation or a bunch of something.
Figure out like impulse. What would our impulse calculation be?
Time to stop multiplied by force of friction.
So that would give us like how much stopping impulse power we have. Yeah? What do you think is, how fast can your car stop? Like what's the acceleration that your car can stop at? There's one question. This was a friend of mine pointed this out. He's a civil engineer in Pennsylvania. He's like, if you don't know what you're doing, just look at something that's already been done and figure out how they did it. They probably had a reason for it. So let's think about like when you stop a car, what's the fastest the car stops? If it's already stopped? Well, let's say you're moving and then you stop the car. Yeah. How fast can it stop? Do we know max deceleration? I mean, I know acceleration it can be positive or negative, but in this case. Not sure. Instant? Well, it's got to slow down. Like even if you're moving slow, I don't know, 10 miles an hour. How quickly can we stop? Second? 1 second, 10 miles an hour. 1 or 2 seconds. 2 seconds. Stopping time.
Well, according to Google, at 7 miles per hour, which is roughly 3.1 meters per second, it takes 10 to 15 feet on a dry road to slow down. It's not good. It's not easy for us is roughly 7 miles per hour. So 10 to 15 miles, or 10 to 15 feet, which How would I calculate this?
Velocity final squared minus velocity initial squared equals 2 times acceleration.
Acceleration would be calculated.
I know you don't like uncertainty in an engineering classroom. That was the whole point of this thing, was just get you to think about, like, what would you do with this thing? Like, how are we supposed to solve it? So one idea was just bigger is better, right? Make this 100. What if it's 100 times more than that initial, like one Newton? We figured out it will stop it. It takes a while to stop it. Is it linear? Is it going to stop it in a quarter of a meter? Maybe, yeah.
Why not?
I don't. That's why I'm asking. How far will it go, and then also, how long does it take to stop? If we make it 100 times that force. So one guess is that everything just divides by 100, 100 times x, so this is 0.25. And then this becomes, or no, that one becomes bigger, right? Is this 20 meters per second squared? What do we think? Is that right? Are you thinking through it or just hoping that I give the... Try it out. Is this, are these two numbers right? 100 newtons? What happens? What happens? Different numbers? Okay.
I'm solving for stopping this.
Okay. Yeah.
It's someone with discussion. I mean, it's just like how far is that go? It falls.
Acceleration.
The first 3 letters, yes. What comes after this?
So, in theory, if given a solid concrete floor,
Yeah.
what would we call the floor stand?
That would be like pushing on. At least if you're saying that it's completely solid.
Oh, look, this is pushing up, the floor's pushing up.
Yeah.
When that's not the fastest.
That would definitely stop it even faster than if you have
Just because
So, you pulling.
Yeah.
That's just stopping off the fastest.
Stop it.
Using kinetic equations of the final minus the initial equals 2a delta x. We then said, oh, the final is 0. What? That's acceleration. The final is 0, so we can so you get 2a delta x over, and then you solve for delta x, you're getting the initial squared divided by 2a equals the initial x. Actually, you should have a negative to where that negative. And then that acceleration, we can then solve for the third derivative of this equation, which is 2g over 2 minus and figure out x. Plug that in for a and solve for n. So then this equation has we know for we don't have an equation. Then we have that distance
is the time to stop for 1.46. Yes.
Did anyone
Alright, and then what's the force?
find
That's two,
next step here?
4, 1, 5
I know.
times 1, 5.
It's been a long week. Okay, so delta x is 3.1 squared over 2 times 20 9/2 times 20. What's 9/40? Is that right? 0.23 meters? That's what I got. Something like that.
Yeah. Force times the time that that force can so time to stop times 2.
So another question came up of like, what if this thing just like hits the floor and really if it hits the floor it's gonna like bounce off, right? Like some kind of, but what's the impulse of just like coming and hitting the floor? If it just hits the floor, different ways to think about it, but do we want to say it bounces or no bounce? That's up to you. No bounce? No bounce? No bounce. All right.
Luke, I got twin.
So at least upper limit of like how fast this thing can stop would be, we go from a constant speed, from that like initial speed, hits our stopper, and it just comes to an abrupt stop. So if it's anything more than 0.31 Newton seconds, then it's as if it's hitting a concrete floor. It's just like slamming into this floor and coming to a stop. Or something, some kind of floor like that, where it's just stopping. Oh, are we? Yeah, we only have like 30 seconds left.
When I calculated the stopping time for stopping 1 meter,
Yeah,
I made a 0.91.
0.91 Newton seconds? Really?
Yeah, because when it's 3 times the normal force, and 1.41 1 Newton normal force, and 0.5, and the time to stop was 0.6 per second.
So that's, is it F over delta T or F times delta T?
F times delta T.
Yeah, F delta T. Yeah, it tells you average force over a time. Yeah. Yeah, it's a good question. Because that's what I get of like maximum. Yeah. So we. And this is kind of the case where it hits the floor. I guess it's not concrete, it's more like carpet, where it hits the floor and just comes to a stop. So we could use this as a limiting case of like how much impulse we want. Okay, thanks a lot. Come back on Wednesday, stronger.